Hi, welcome to 16th session on group theory, third session on group homomorphisms. So you can see that we are spending a lot more time on group homomorphisms because one of the most important concepts in modern mathematics is given two objects of the same structure, what kind of maps preserve the structure. That's a very important thing. Okay, so it's better to look at it very carefully, understand it in depth. Okay, so let us look at a few more things. So in the last section, we said that if G to H is a group homomorphism F, then we define what is meant by kernel of F. That was set of all G in G, so that F of G is identity element in H. I will not denote by EH and EG here. I will only denote E. The context should make it clear. Right, so this is what we want to look at. And we also remember the reason why we did that. Okay. So let us fix an A in G, ask the question, what are the elements G in G, so that f of G is same as f of A. That is, f takes value fa at G. Right? This is what prompted us to define kernel of f. Please recall. Okay. Now notice that if f of A G equal to f of A, that means f of G into f of A inverse is identity element of H, of course. This is also equal to f of A into f of G inverse is identity. Okay, I'm equating. This means this is upon only if f of G into f of A inverse is identity. That is upon only if f of G A inverse is identity. And this similarly f of A G inverse is identity. That means G A inverse must be in the kernel. Let K be the kernel. Okay, and so similarly A G inverse in the kernel. Okay, pause. This is how we introduce. Right. So that means my G must be in AK. Right? G A inverse belong to this. That means you multiply both sides by A. That is G A inverse equal to some K in K. Therefore multiply G both sides by A, K into A, but that means it is in Ka. Sorry, I said AK, this is Ka. And similarly AG inverse in K, that means AG inverse is some element K. This may not be the same K, some other K. Multiply both sides by G, that means A must be in K G, that is multiply this by K inverse A, is in G. That means, and remember, since K is a subgroup, this is an element K, therefore G belongs to K. Am I getting something different? G A inverse in K, that means we multiply G A inverse equal to K, therefore multiply both sides by A, therefore G belongs to Ka, therefore it's Ka. And here K inverse A, K is allowed to vary. Okay, so let me recall. So what are the conditions? G A inverse is in K. Other one is A G inverse is in K. Did I do that correctly? Hi, recall why we defined kernel. We wanted to understand given two elements A and B in the group when f of A equal to f of G. Then we found out by after manipulation we found out that is f of A B inverse is identity or f of B A inverse is identity. That's how we looked at the set of elements G such that f of G equal to identity. That's how we defined the kernel. Okay. Now we understand this. This is a very important thing which will permeate in many disciplines. So let us try to understand it a little more carefully. So I want to look at fix A in G. Of course, F is a group homomorphism from G to H. Okay. And fix A. Then I want to look at the set of our G in G so that f of G equal to f of A. I want to understand this set. Okay. So let us try to understand. This means if f of G equal to f of A, okay, that happens if only if f of G into f of A inverse is a identity. This identity element is of this H. This if only if f of G into f of A inverse is identity. This is if and only if f of G A inverse is identity. This is if and only if G A inverse belong to kernel K, where K is the kernel of F. Right? That means this is if and only if G belong to KA. Right? What is KA? Let us recall KA by definition is set of all x times A as x varies over K. Right? And similarly AK will be okay set of all AX as x varies over K. Okay, so this is KA. And in a similar fashion, we can see f of G equal to f of A if and only if I can multiply the other way around. Okay, identity equal to f of A into f of G inverse. That is if only if f of A into G inverse. Okay, is identity. That is if only if, maybe I can do other way around. Let me look at it in a minute. A G inverse is in K. Right? That is if only if A G inverse is some K in K. That is if only if A equal to Kg, right, for some K. Right? So let us not do that. So let's slightly do differently. Therefore, this if only if identity, if only if identity equal to f of A multiply f of A inverse f of G is identity. That is if only if f of A inverse G is identity. Right? If only if A inverse G belong to K. Right? Or let us again same thing. F of G into f of A inverse is identity. This f of G A inverse is identity. This is if only if G A inverse belong to K. That is if only if G belong to KA. Yeah, very good. I hope they are different, AK and KA. Right? Therefore, what you have found is set of G in G such that f of G equal to f of A is given by this or this. So in particular, these are equal, where K is the kernel. Okay, pause, review, proceed. Does this remind you of anything? Something similar you have seen? That is, try to think of it as you want to solve the equation. What is the equation? F is a group homomorphism from G to H, and look, E be the identity element of H, EH if you want. I am looking for the solution of this equation. What are the G in G such that f of G equal to identity. That is the kernel K, right? Now I want to ask a more general question. Fix an A, right? Then I want to know what are the, can I describe the solution set of f of G equal to f of A? I use the word solution set. Does it trigger your memory? Yeah, I will. I'm at least some of you must have got it. Let me explain that thing. Okay, let us recall solution of. Okay, suppose I have a linear system A j x j j equal to 1 to n, 1 less than equal to I less than equal to m equal to some bi, right? So where A j's are real and bi's are real, right? Then this is the system of linear equation. Okay, then associated homogeneous system sum is summation a j x j j equal to 1 to n is 0 for 1 less than equal to I less than equal to m, right? Now suppose yes be the solution set of homogeneous system. So this is, let me write x equal to, I will write it as a column x1 into xn in Rn, so that, okay, summation a j x j j equal to 1 to n is 0 for 1 less than equal to I less than equal to m. This is the solution set of the homogeneous system. Okay, similarly let us look at set of all x in Rn. Again I am writing as a column vector summation a j xj j equal to 1 to n equal to bi 1 less than equal to I less than equal to m. This is the solution set of the non-homogeneous system. So what we have learned is, suppose I have some, let us say C equal to C1 to Cn is an Rn, is a particular solution. That's a word you use, that is C belong to S of H. Then we know how to describe S. S equal to C plus SH. This is set of all C plus X, okay, where S is in SH. Okay. This equation you might have seen in your linear algebra course, and also when you are doing ODE, okay, you would have done these things. Okay, you have a linear ordinary differential equation, then if you know the particular solution you can of ODE, then you know, and you know the solution set of the homogeneous corresponding homogeneous system, you can write down the solution set of the original non-homogeneous differential equation. These are similar, right? Something similar is what we are showing. What have we shown? In the case of homomorphism, see, now when I want a particular solution, suppose I take something like H in H. H is an element in the sub codomain group H. H may not be in the image of F. Therefore, you start with some element which is in the image. That's why we started with A. Okay, that means A is a solution of F A equal to H. Are you following me? Let me explain. Suppose H is in H, I want to look at the solution set of G in G such that F of G equal to H. Okay, unless H happens to be in F of G, okay, this set will be empty. If H is not there, this will be empty set, right? Therefore, suppose H is in F of G, that means there is at least one A in G such that F A equal to H. That is, I have a particular solution of this set. Okay, particular solution of the set. Namely A, this is the solution. Okay, then I know all the solution. This set, okay, this solution set is nothing other than take the particular solution. And here the binary operation is not addition. If the group is additive group, then I will write. Otherwise, it is AH, or which is also HA. Okay, that's all we proved. Pause, review, proceed. Caution. If H is a general subgroup of G, okay, or K, let me say, just as any subgroup, okay, there may exist A in G so that A times K is not equal to K times A. So this is something special about kernel. Okay, we will look at examples later. Actually, it's easy. Okay, but I don't want to spend time now. I want to concentrate on what is important. Right? Okay. Now let's look at a second item. Suppose G is abelian. Right? Remember, if A and B commute, then we have seen AB power n is A power n, B power n, right? So this suggests, therefore, for fixed n, an integer, okay, when n is 0, it will be identity. Okay, let us look at f of A equal to A power n. This is a group homomorphism. Right? Because of this. Right. So let us look at a very specific example to understand, okay, a specific example, concrete example. Okay, let us look at G equal to Z15 units in this. I will also denote by 15 star. Okay, this set of elements M and Z15 so that there exists a K in Z15 so that M times K equal to 1 in Z15. That is the albeit multiplicative inverse. We know what are they. They are, this happens if only if M is relatively prime to 15. Therefore, what is G? 1 is relatively 15. 2, yeah, is 2 relatively 15? Sorry, relatively prime to 15. Yes. 3 is not. 4 is there. 5 is not. 6 is not. 7, yes. Yeah. And 8, yes. 9, no. 10, no. 11, yes. 12, no. 13, no. 14. So 1, 2, 3, 4, 5, 6, 7, 8 elements. Okay. Right. Now I want to look at the map n equal to 2, f of g equal to g squared. Okay. We know this is a group homomorphism. So I want to identify what is the kernel of f. Okay. So what is that? I want to look at what is 1 squared. 1 squared, of course 1. 2 squared will be 4. That won't be there. 4 squared will be 16. But 16 is 1. Okay, mod 15. And 7 squared is 48. It is not there. 8 squared is 64. That is 60 plus 4. That is not there. 11 squared is 121. That is 128 times 5 plus 1. Therefore 11 is there. And 13 squared is 169. And 114, that's not there. Right. And then let us see 14. 14 squared is 140 plus 56, 196, 14, 46, 35, therefore it's 1. Yeah. So kernel of this consists of 1, 4, 11 and 14. Okay, I give you time just to make sure that you follow this. Okay, please check. Now I want to understand what is the image of f. So these things are ruled out now. Okay, I don't want to consider, they are not going to contribute to find the image because these will go to identity 1, 4, 11 and 14. So I only have to look at 1, but remember image will contain always the kernel, therefore identity, therefore 1 will be in the image and 2 squared will be 4 and 7 squared will be 49, 3 times 15 plus 4, therefore again 4, and 8 squared will be 64. 64 is 4 times 15 plus 4, therefore again 4, and 13 squared we already found out, it is 1. 13 squared is 169 divided by 15, 1, 49, 4, therefore it's also 4. So image consists of only 2 elements, right? So pause, review, proceed, right? Now again observe something interesting. What is number of elements in G? 8. What is kernel of F? It has 4 elements, and image of F has 2 elements. So what do you think? Okay, I have kernel, that is, if you want to think of is, I use a word nullity, image which is rank, range. So image is range, and what we found is the number of elements in the domain group equal to the product of the number of elements in the kernel and number of elements in the image. It's something like a rank nullity theorem. Yeah, but we will prove it little more in a more general setup little later, but just observe this just for fun. So this reminds us of okay. Yeah. Now let's look at another example 3. So, suppose G is cyclic. H is any group, right? Suppose F is a group homomorphism from G to H, right? Something is very, suppose G is generated by A, okay, right? That is G equal to A power n as n varies over Z, right? Okay. Now, do you see something interesting? Any element x in G is of the form x equal to A power n, right, for some n, right? Therefore, what is f of x? F of x is f of A power n. But since f is a group morphism, it is f A power n. So, what does this say? What is its significance? It says that f is completely known if we know f of A. This particular element in H, if we know this, we know that. Why? Because give me any x is of the form f of A power n, therefore f of x will be, right? Suppose f of A equal to b in H, and if x is an element in G, then x is A power n, therefore fx is b power n. That's it. Yeah. So pause, review, proceed. Okay. Again, does this remind you of something? Suppose instead of G and H, let us replace it by V and W vector spaces. If F is a linear map, linear transformation from G to H, and if I know the value of F on a base of V, then I know F completely. Yeah, do you remember that? Yes. If we want to assume that V is finite dimensional, V1, V2, Vn is a basis of V, then any x in V can be written as summation A, Bi, where A is a scalar. Therefore, F of will be summation F of A times, summation, F of summation A, Vi, that is equal to summation A times F of Vi. But I know F of Vi, therefore I can write it down. Yeah. So again, something similar. Here there is a constraint. What is the constraint? The constraint is that if A is of finite order, then F of A will be of finite order and its order must be a divisor of n. Okay, it's not free. You understand? What do I mean by that? Please think. Okay. Otherwise, you will think that it becomes another question in linear algebra, so I don't want to do that. Yeah. Because there, in the linear algebra setup, I can take any W1, Wn in W and let F of Vi equal to Wi. There is no constraint on W1, W2, Wn. Any choices will do. But in this case, F of A must be, okay, an element of H whose order must be a divisor of this. Therefore, if I choose F of A equal to B, the order of B is not a divisor of A, then that's not going to define a homomorphism. Okay, maybe it's confusing. It's okay. Think about. Okay, so let us use this to ask a next question. Suppose I look at Zn and G is a cyclic. Let us say G equal to A, and number of elements is also n. Okay, can you think of a natural homomorphism? Obvious, because what is Zn? Zn is 0 if you want to put 1, 2, n minus 1 and n which is 0, and G is A squared, A to the power n minus 1, A to the power n is E. So what is the obvious map you can think of? I can think of F of 1. Okay, if you want 1 is 1 mod n. Okay, this is A. Therefore F of K will be A power K, where 0 less than equal to K less than equal to n minus 1. Is it clear? And it's a group homomorphism. Okay. Okay. So let us look at little more carefully this one. Okay. I want to check it's a group homomorphism, but let's do it slightly differently. Again, let's look at, okay, suppose G is a cyclic group generated by A and mod G is, let us say, n, and H is any group. I am looking for a homomorphism G to H. Therefore, it's enough to know what is F of A. Suppose F of A is B. This B cannot be arbitrary because order of B must divide n, right? So, let B be such that order of B equal to n. Okay, then define F of A equal to B. So I want to say, using this I can define a group homomorphism. Then we have a group homomorphism F from G to H such that F of A equal to B. Is the question clear? Yeah. So G is a cyclic group generated by A, H is any group Then I want to define a group homomorphism of G to H. What do I have to look for? I look for any B in H such that order of B is a divisor of N. Right? That is the order of A. Okay. Then I want to say there exists a homomorphism F from G to H whose value at A is B. Right? How am I going to define? Think carefully. So obvious way is I want to define. How do I define? Right? To define f of a to the power k equal to f of a power k, which is b power k. If it is a homomorphism, it has to be this. Therefore, define b power k. Because again, compare this result with v to w, and v1 to vn is a basis, and w w1 wn elements of w. Then there is a unique homomorphism f from so that fi of v equal to wi, unique f from b to w. It's a linear. Okay, something similar is what I am doing. F of a power k equal to b power k. So I want to say this is well defined. This is well defined, and then it's a group homomorphism. Two things I have to check. Why it's well defined? Suppose start with any element x and g, then x I may be able to write something like a to the power k. Also I may be able to write a to the power r, where k and r are integers. Right? And since order of a is n, therefore this means a to the power k minus r is identity. Therefore that means n minus divide k minus r. Therefore, okay, I can write k equal to, let us say, r plus some mk. Right? Therefore k minus r is a multiple of n. Sorry, n. Multiple of n. Yeah? Therefore k is r plus mn. Is that clear? Therefore what is, okay, therefore my x is a to the power k, which is also equal to a to the power r plus mn. By law of indices, a to the power r into a to the power mn. Therefore f of x, okay, what is f of r? Okay, I have to check whether it is equal to f of a power k. But what is a to the power r? F of a to the power r is f of a to the power r is f of, I can do it here itself, a to the power k, right? Yeah. Sorry, let me see, f of a to the power k. A to the power k is f of a to the power r into the a to the power mn, which is f of a to the power r into f of a to the power mn. But that is equal to f of a to the power r into f of a to the power mn, that is f of a to the power r, that is f of a to the power r into f of a to the power n and to the power m. But this is b to the power r, this is identity, that's what identity, it's b to the power r. That is f of a to the power r. Yeah. So I have checked, proved f is well defined. So if this is the first time you are coming across well-defined notion, you should understand. Start with any element x in G, which is a cyclic group generated by A, then x must be some power of A. Okay. So somebody may say x is a to the power r, somebody may say x is a to the power k. Then I will define, the first person will define f of x to be f of a to the power r, which is f of a whole to the power r, which is b to the power r. The other person will define f of x equal to f of a to the power k, that is equal to b to the power k. So we will have to make sure whether b to the power k equal to b to the power r. You understand? That is what is meant by well defined. We checked it. Please understand. If you are a BSc student, this may be a little trickier. Go slow, review it again. Okay? Replace these words again, you replay, understand. Next, it's a group homomorphism is clear because start with any two elements x, y, and g. They are of the form a power r into a power s. X is this, y is this. Therefore, what is x times y? By law of indices, a power r plus s, right? But what is f of x, y? F of x, y is f of a r power s, but that is b r power s, but by law of indices b power r into b power s, but that is f of a to the power r into f of a to the power s. That is f of x into f of y. Okay, therefore it's a group homomorphism. So group homomorphism. So try to see that without checking well-definedness, I can actually use law of indices and do that. But then the crucial point is well-definedness. I do not know, okay, if my x is a to the power k as well as a to the power r, f of x is well-defined. That is b to the power r is same as b to the power k. I want to ensure. After that only this checking that it's a group homomorphism is, which is trivial. It follows from law of exponents. Please review. These are the small subtle things. Okay, one doesn't spend time on such thing. That's why I took a little more time to explain this. Okay, go slow, learn thoroughly. Now we go to the last important thing. Okay, now I want to understand all group homomorphisms from Zn to Zk. Right? So from the earlier one, this is a cyclic group, let us say generated by A equal to 1n. Okay. Therefore, if I want to define f of A equal to B, which is let us say m k and zk, then the first thing is order of B must be a divisor of n. Okay. Right? So choose m such that order of m k divides n. Okay, just to make you understand, you should not get confused. Let me look at Z12 to Z15. Right? Then I want to define f of 1, 12 equal some m. Right? 15. What should be this m? The order of m. See, what are the divisors of 12? 12 is 2 squared into 3. Therefore, divisors are 2, 4 and 3. And hence all the property. Right? Are you following? Now, therefore, I have to find an element whose order is either 2, 4 or 3, etc. So, what is the possible thing? Remember, 15 is 3 times 5, right? Therefore, the common thing seems to be only 3 because if m is an element of this, its order we have seen is a divisor of 15. Okay, therefore, it should be a divisor of here, that should be a divisor of here, therefore, it clears it is order must be 3. Therefore, what should be my m? M may be 5 or m may be 10 because 5 plus 5 is 10 and 5 plus 5 plus 5 is 15, which is 0 in Z mod 5. Therefore, the subgroup generated by this 5 in 15 is 0, 5 and 10, and let's look at the subgroup generated by 10. That is 10, that is 20 is 15 plus 5, therefore is equal to 5, right? And then 5 plus 10 is 15, which is 0. Therefore, it's again the same subgroup. Are you following? Pause, review, proceed. Is that okay? Right. So, now what I have done is, so let us go back to the general case. Zn to Zk. Right? So, choose m. Let m be such that order of mk is a divides n. Okay, now what does that mean? Now remember that means n times mk must be 0, but n times mk is same as nm k is 0. That means nm is congruent to 0 mod k. That is k must be divisor of nm. You follow that? Right? So there are two conditions on m now. One, order of divides n. Two, k divides n times m. Okay. Suppose we found, suppose m satisfies both conditions. Then we define, let us define f of j mod n to be j m mod k. You understand this? That is f of 1 mod n is k. That's how you define and extend it. Okay. And is this a group homomorphism? Yes. Okay. How did you know that? That is because f of Rn plus Sn is it equal to f of Rn plus f of Sn. That is, this is same as R times m k plus S times m k. This is the question I want to look at. Right? But that's very easy. This we had already seen. Right? Remember, we're defining this is well defined. First, this is well defined. We had already seen it. Why it's well defined? Go back to the earlier one. Okay. If G to H, G is cyclic. If f of A is B, if order of B is a divisor of order of G, namely order of A, then this is a well-defined group homomorphism. Therefore, this is a well-defined group homomorphism. Okay. Pause. Review. Proceed. Let us look at the example which you looked at, a concrete example. Z12 to Z15. So, our A is 1 here. And our B here is either 5 or 15 or 10. Right? Let us start with 5. Right? So, I want to define F. Okay. So, what should be the kernel of F? Okay. Right? Now, let us look at see, now kernel of F of course will contain 0, 12. Right? 1, 12, no, 2 goes to 10, 3 goes to 5 times p. You understand that? F of 3, 12 goes to F 3 times 5, 15, that is 15, 15 is 0 in Z15. Right? And similarly, 4 is, where does it 4 go? 4 times 5 is 20, that goes to 5. And okay, maybe it will be good to write image also at the same time. So 0 goes to 0. Okay. And 1 goes to 5. And 2 goes to 10. 3 goes to kernel. 4 goes to 4 times 5 15. Therefore 15, 4 times 5 is 20. 15, which is 5. Therefore it again goes to here. And 5 times 5 is 15. 5 times 5 will be 25. That goes to 10. And 6 times 5 is 30. 30 also goes to 0. Therefore 6. Right? 6 times 5. 6 goes to 6 times 5. That's 30. 30 is 3 times 15. 2 times 15. Therefore 0. And 7 times 5 is 35. Therefore that goes here. And 8 times 5 is 40. That 7 35 7 8 40. Therefore 40 is 2 times, it goes to 10. Okay. And 8 times 5 I done. 9 times 5 is 45. That goes to 0. Okay. Are you following me? Then I have to look at 10. What is 10? 10 times 5 is 50. That goes to 3 times 15 plus 5. It goes 5. 11 times 5 is 55. That goes to 45 plus 10. That goes to 10. Yeah. And then 12. 3 6. Oh, I forgot 9. So what 9 goes to 45. That also goes to kernel. Okay. So this is the image. Okay. I went through fast. Please go through it carefully. Okay. See, this kind of very concrete examples, many algebras don't do that. Students learn pure abstract thing. Even the good students love abstraction. But in an interview, when you ask such concrete things, they are at a loss to work with. Okay, please. Okay, become comfortable with the concrete examples also. Right? Okay, come back. So what I have shown now? I have shown that kernel is this. It's a subgroup generated by. So when f of 1 in I think 12, right? Or 5, I don't remember, yeah, 12 is 5, 15. Then the image is kernel of f is a cyclic subgroup generated by 3. And image of f is cyclic subgroup generated by 5. Remember, kernel and image both must be subgroups, but these are cyclic groups, therefore there must be again cyclic groups. That's why I know I have to find out. Number 1. Do you understand? Then next, what is the number of elements here? Number of elements is 4. Number of elements is 3. And 4 times 3 is 12. That is number of elements in Z12. Right? This is okay. Kernel of F times image of F equal to number of elements in Z12. Our rangularity theorem kind of argument. So please go through the example. I know it. Many of the things are very taxing. Usually it's never done even at MSc level. But if you love mathematics, if you hope to pursue research career in mathematics, it's better to go slow, learn these things in depth. Later you will see when you go to more abstract things or higher aspects of algebra, you will be able to work faster and you will be more confident. Okay, I hope you enjoyed this. Stay tuned. In the next lecture, we will start isomorphisms in earnest. Okay, thank you. Stay tuned.